Good morning, my YouTube viewers. It's Crystal here. In this video, we're going to cover another non-parametric test, and this is the Kolmogorov-Smirnov test. It is a non-parametric test of goodness of fit test that compares two cumulative distribution functions, measuring the maximum vertical distance between them. And basically, what you're doing is you're checking to see if two vectors or two lists or two columns of data are of the same distribution. And I use this test a lot in machine learning. So whenever I'm doing a Kaggle competition, if I want to see if two columns of data are from the same distribution, then I'll do the Kolmogorov-Smirnov test. And then so what this test does is a one sample KS test measures the sample CDF of a theoretical distribution against such as a normal or exponential. So it's just measuring a column of data or a vector or distribution against a normal distribution or an exponential distribution or any other distribution that you decide to name. And then a two sample KS test compares whether two samples come from the same distribution, and that's generally how I use the test in machine learning. The KS test for a null hypothesis where the distributions are identical, or an alternative hypothesis where the distributions are different. So what we're going to do is we're going to go over and got a program of the Kolmogorov-Smirnov test, and we're going to review the code. So we're going to compare the two distributions using an EDF and an ECDF, and that's an empirical cumulative distribution function. It's a statistical tool used to describe the distribution of observed data without assuming an underlying theoretical distribution. So first thing we're going to do is we're going to set our seed. And the reason why you set your seed is because every time you run the program, it initializes the variables to the same values. So you type set.seed brackets 1, 2, 3. You can put any number you want within the brackets. And then we're going to simulate two samples. So X is going to be a randomly sampled normal distribution of 100 samples with a mean of 0 and a standard deviation of 1. And Y is your randomly sampled normal distribution of 100 samples with a mean of 0.5 and a standard deviation of 1. So we're going to perform the Kolmogorov-Smirnov test. So KF result becomes KF.test brackets X, Y, and we're going to look at the result of the test. And the result of the test is an asymptotic two-sample Kolmogorov-Smirnov test. The data is X and Y, your D is 0.15, and your p-value is 0.216. The alternative hypothesis is two-sided. So since the p-value is 0.26, that means you're going to fail to reject the null hypothesis. And what that means is there's no significant difference between the distance of the two distributions. And so that's what your null hypothesis means. So now we're going to plot the ECDFs and highlight the KS statistic. So ECDF X becomes ECDF X, and ECDF Y becomes ECDF Y. And your ECDF is the empirical cumulative distribution function, statistical tool used to describe the distribution of observed data without assuming any underlying theoretical distribution. So we're going to create a plot. So plot brackets ECDF X, verticals equals true, do dot points equals false, main, which is your title, is Kolmogorov Kolmogorov-Smirnov test, ECDF comparison. X lab is the label on your x-axis, which is value. Y lab is the label on your y-axis, which is ECDF. Column is still blue, and line width is 2. So we're going to put some lines in there. Lines, brackets, ECDFY, comma, verticals equals true, comma, do dot points equals false, comma, color equals tomato, comma, line width equals 2. We're going to put a legend in there. So legend, brackets, top left. Legend is a vector. It says sample X and sample Y. Color is a vector, which is sample X is assigned still blue, and sample Y is assigned tomato. Line width equals 2, BTY equals N. And then we're going to add the KF statistic, maximum vertical distance. We're going to create a fine grid of X values. So grid becomes sort brackets, which is a vector of X and Y. We're going to compute the ECDF values on the grid. So Fx becomes ECDF X grid, and Fy becomes ECDF Y grid. We're going to find the point of maximum difference. D becomes max brackets ABS X Fx minus Fy. That's the absolute value. IDX becomes which dot max brackets ABS, that's absolute value, brackets Fx minus Fy. And then we're going to put a vertical line in the graph. Segments, brackets, grid, IDX, comma, Fx, IDX, comma, grid, IDX, comma, Fx, Fy, IDX, comma, color equals black, line width equals 2, LTY equals 2, which means it's dashed. We're going to put some text in there. So text, brackets, grid, IDX, comma, Fx, IDX, plus Fy, IDX, divided by 2. Labels equals paste 0, brackets, D equals D rounded to 3 points, and the position is 4. And then so when we run the program, this is the graph that we come up with. And so you can see we've got the Kolmogorov-Smirnov test ECDF comparison. Blue is your sample X. Y, red is your sample Y. And you see that you have a D of 0.15, which isn't very much, gives you a p-value of 0.2106. But let's change the data. So instead of this data being 0.5, let's make the data a mean of 1. So let's change the data and see what happens. I'm just waiting for it to run up. So when we change the data and we see what happens, you see that your p-value becomes 2.267 to the negative 6, which is a really low value. And you can see the distance between X and Y is increased from the 0.15 to 0.37. And so that means that your p-value is less than 0.05, which means you're going to have to go with the alternative hypothesis, which means there's a significant difference between the two samples. So now I'm just going to go back here and change it to 0.5 and run it again. So, and then we've gone back to our original value of the p-value 0.2106, which means that you failed to reject the null hypothesis, and you can see the distance between X and Y is not very big. So what that does is that gives you a visual representation of the Kolmogorov-Smirnov test, and basically I use it a lot in machine learning, so it's a good test to use if you want to see if two vectors or lists or columns of data are from the same distribution. So that concludes this video. The next video is going to be on another nonparametric test, and I hope that you got something out of this video, and I hope that you decide to watch the next video. Bye.